So we're going to do double integration. We're going to introduce the idea of double integration. And mechanically, it's not going to be too bad, especially when we go over rectangular regions. But before we jump into that, let's just remind ourselves of how we got to regular integration, and single variable calculus. Our definite integral then, our regular integral, our definite integral, we approximated it by, we had a bunch of rectangles, we had our curve here, f at x. I was integrating from, or we would be integrating from a to b. And what we did was approximate the area by the sum of the area of a bunch of rectangles. We added up the sum of all the rectangles. Our delta x then was our width of the rectangles, and we usually got that by taking the interval length and dividing by the number of rectangles. That would give us our width of the rectangles. We had a constant width of rectangles. And this f of f star, so we're trying to get the area of one of these rectangles. That would be the width, delta x, times the height. And the height of each rectangle, we chose where to evaluate the height. So this is our f of x star. X star just means special x. So in this case, the picture that I drew, they're all on the left-hand corners. But you'll remember we could have chosen right-hand corners or center points. In the end, for an approximation, we had to make a choice about left-hand corner, right-hand corner, midpoint. But when we took our limit, right, when we took the limit as the number of rectangles goes to infinity, as n goes to infinity, the delta x goes to 0. So we've written it here, n goes to infinity, but it's the same thing as writing delta x goes to 0. The number of rectangles goes to infinity, the width goes to 0, and this delta x morphs into the dx here. That's the dimension that shrinks. And then our limit of a sum becomes the integral. There's a quick kind of overview, reminder of what we did in single variable calculus. Now, in double integration, multivariable calculus, we're going to have two dimensions, an x and a y. Before we jump in there though, this was area. And if you think about it, let's say we measure height in meters. So the y value was measured in meters. And this x value was measured in meters. When we get the area, it's meters squared. We integrate over a length, a height over a length, and it's like multiplying them. When we integrate double integration, we're going to have, I'm trying to draw in 3D here though, so we have a height over an x and a y, meters, 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 we're getting a volume under a surface. That's where we're going with this. All right, so let's go back to what we have mechanically. And again, mechanically, these are not too bad, although I always think it looks impressive, right? When you're doing your homework, double integrations and stuff look like you're doing high-end calculus, but really the mechanics of it is fairly straightforward. So if I'm doing a double integral, we're integrating from a to b some function dx, and we can put in here some function dx integrating with respect to x, subbing in the top number, subbing in the bottom number. If this is a dx, then this is x equals a and x equals b. We get a formula. There won't be any more x's in it because we'll have subbed in a and b for x's. Then we integrate any leftover y's from y equals c and y equals d and get an answer. We'll look at this mechanically, but I want to approach it as this limit sum idea. So I've replaced both integrals. They're double integrals, but I've replaced each one with limit sum, limit sum. So n is the number of rectangles in the x, chopping up the x coordinate, and m is the number of the dx or the dy in the y coordinate, let's say. It's going to be easier if we take a picture. So let's start, or make a picture. Let's jump right in on an example. So I want to integrate under a surface to get a volume, because this dx would be in the change in the x would be in meters, the change in the y would be in meters, the height would be in meters, 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 meters cubed. So here's our function, xy divided by 4 plus 1. And the footprint is this rectangle. X's go from 0 to 3 and y's go from 0 to 2. This is what we have. So here x goes from 0 to 3, y goes from 0 to 2. This surface is given by this roof of the function. This roof of the volume is given by the function x times y divided by 4 plus 1. And the way that it's been gridded off, each one of these rectangles, I'm going to think of as a rectangular prism. And I'm going to get the volume of that rectangular prism. The volume of a rectangular prism, length times width times height. So let's make a decision where we're taking the height from. We've got like 4 corners, or we could do the midpoint of the rectangle. So we've chosen then, well, it's chosen here, left bottom corner rule. So let's see, we'll take a clip of this and we can draw on it. So left bottom. So we're evaluating at this corner for this rectangle, this rectangular prism. My drawing is not good. No, insofar as that it's terrible. But, and then this wall is one of the things which is already a straight line. So that's supposed to be a rectangular prism. Let's draw it out here a little better. So I'm trying to find the volume of that shape. This is where we're getting the height. So this is our x star, y star. X star, y star, our bottom left corner. And we're plugging it in. So the height is whatever the function with that particular point plugged in, times the area of the bottom. The area of the bottom is going to be the delta x and the delta y. So the volume of this shape is going to be the height times delta x times delta y. And we're going to sum that up over, we've decided to split this up into 10, and this is up into 7. So our delta x in this case is 3 divided by 10.3. Our delta y is 2 divided by 7. So the way that we've written it, our delta x is 3 over 10, and our delta y is 2/7. And all we got to do then is, so the footprint here is delta x times delta y. The area of these rectangles, the rectangular footprints are all the same. And I've got the sum. So I'm going to sum up, let's make the i's for y and the j's. So I is going to go from 1 to 10, because there's going to be 10 of these x values. And the j is going to go from 1 to 7. And when I sum up this double sum, this will be the sum of all of the heights taken on the bottom left corners. And this will approximately be the volume. And all we're saying is, when I take the limit as the number of rectangular prisms go to infinity, so I have to take replace this 10 with an n and let that go to infinity, replace this 7 with an m and let that go to infinity, that the volume is then going to become equal to, now that function, our delta x goes to a dx, our delta y goes to a dy, those are the dimensions that shrink to 0, x goes from 0 to 3, y goes from 0 to 2, and now all I've got to do is mechanically figure out what that integral is. And that'll be the exact volume. Limit definition of an integral, but now it's a double integral. And if I think about it, let's just group this for a second. If I only look at this, because it looks like I made a great big jump there, right? But if I only look at this, then that's the straight, if I take the limit as n goes to infinity, this is equal to the integral from 0 to 3, the function f of xy dx. That's just straight limit definition. And once I've replaced that, then I can think of the red thing as its own little function, and then the delta y to dy integral falls out from the limit definition. So if I'm approximating it using the left-hand end rule, that's what I get. If we want to actually figure it out, though, so I can take this as my I'm not taking the limits yet. I'm just using those 70 and 70 rectangles. So dx, x goes from 0 to 10. There was 10 divisions here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 7 here. 1, 2, 3, 4, 5, 6, 7 for the y's and the x's. Our function, our actual function then, is going to be let's do it this way. Sub j our function is plug in the xy, divide by 4, add 1 to the whole thing. So here's using the rectangular prisms. I would get an approximation of the volume. Now let's just look at the shape for a second, as here. I'm using sort of the bottom corner, so my true volume is actually, because of this particular shape, the true volume numbers looks like it's going to be above. If I would have chosen top right corner, then the true volume would have been below. If we would have chose midpoint, it might have been more closer, more approximate, but since we're going to let the limit as m and n go to infinity anyway, so that's approximately equal to, and so the reason why there's approximate is because this is only going to 7 and 10, where this is limit as n goes to infinity, and this is equal to, we got our double integral, the function, and the inside sum has to do with the x, so the inside integral are the x endpoints from 0 to 3. The outside sum has to do with the y, the delta y. So that's why the outside integral has the 0 and 2. Now let's just evaluate this. Let's get a number for this. Well, what I'm doing is thinking of this inside piece as its own thing. Inside the square bracket, it's just integrate with respect to x. Y is a constant. So let's integrate this function with respect to x. If y is a constant, that y over 4 is a constant. This is just going to be straight, add 1 to the exponent, divide by what's up top. This 1 becomes a 1x because I'm integrating with respect to x. So there I've integrated with respect to x, and now I'm going to go sub in the top minus sub in the bottom. So I've integrated. I'm still inside that square bracketed piece. So this is going to be, this 0 and 3 are x's. So it's going to be sub in the top, so sub in the 3 for x, so that'll be 9 plus 3, minus sub in the 0 for x's, so 0. Now what's left over then is just plain integration, single integration with respect to y. So integrate the y, that's going to be 9y squared over. So we're going to be add 1 to the exponent, divide by what's up top, plus that 3 is going to be integrated to 3y. Sub in the top minus sub in the bottom. The y's go from 0 to 2. So we've got sub in the 2, so that's going to be 4. So that's 9 over 4 plus 6. Units cubed if we're thinking about it as a volume. Now mechanically not too bad, but let's go back to sort of first principles here. And keep in mind too that later on when we're doing the homework, we're going to start at this stage. This limit definition is only introduced there so that we can make the connection between our limit definition of an integral from single variable calculus and how it translates up here to multivariable calculus. If you look back though, let's go back to our picture. Now, when we were integrating, I just wrote this down and I wrote delta x and delta y, just kind of out of habit. But I could have wrote delta y and delta x. These delta x's and delta y's, they morph as the area of the rectangle goes to 0, or another way to think about it is the number of rectangular prisms go to infinity. Then these delta x's and delta y's change into the dx's and the dy's. But I could have written it as delta y and delta x. I could have thought about the y's first. So some people think of this as a delta A, change in area. So I could write dx dy, or I could write dy dx. They're both a dA, change in area. They're equivalent. Yeah, I got to be careful when I say that. Yes, they are equivalent, but they change the endpoints. So when I'm setting up these integrals, I'm choosing to do dx dy first, or I could have chosen dy dx. Let's do that. So I'm going to set these up. I'm going to redo this question, but I'm going to write this as dy dx. I'm going to do y first. So I can just switch these. I'm using this idea here that dx dy, that's little change in x times little change in y is little change in area, or I could have written it as little change in y times little change in x. Oh, but I got to be careful. I'm integrating with respect to y's first. Y doesn't go from 0 to 3. Y goes from 0 to 2. So I need to switch the endpoints. The inner integral has to do with the dy. The outer integral has to do with the dx. So this is x equals 0 and x equals 2. This is, no, this is y equals 0. So let's separate that up. That's the lowest value of y. The y's start on that y equals 0 and go to this y equals 2. The x's have to do with the 0 and 3. If I switch the dx dy to a dy dx, I have to pay attention to the endpoints. Now it's straight integrate. Let's do our integration. Let's see what we get here. I'm integrating with respect to y. So that's going to be y to a y squared. Add 1 to the exponent, divide by what's up top. This 1 becomes a 1y. So now I've integrated with respect to y. So it's going to be a sub in the top minus sub in the bottom, but they're y's. So sub in for y. If I make y equal to 2, that's 4 over 8. That's going to be, make this a half here. A half here. 2. And when I sub in the 0, it's minus 0. So now I've done the sub in the top minus sub in the bottom. Now, finally, let's just integrate with respect to x. This just looks like single variable calculus. Integrating x over 2, that's going to be an add 1 to the exponent, divide by what's up top, so x squared over 4 plus 2 goes to a 2x, and it's a definite integral, so I'm going from 0 to 3. Sub in the top, 9 over 4 plus 6. Sub in the bottom, 0. I get the same answer, yeah, because the volume's the same. So you should get the same answer whether you do dx dy or dy dx. But I have to, my point is when I switch these dx to dy, the endpoints have to match however you set it up. They're both a dA, but if I do dx first, then the inner integral has to be x's. So if I've got a double integral, it's over a region, and we split that region up into little rectangles, and as the number of rectangles goes to infinity, the area of those rectangles, the dA, goes to 0. And we saw that we can write the dA as a dx dy or a dy dx, and when we pick one, say we pick dy dx, then the y is first and we have to make the inner integral the y's. And it comes out of our limit definition of an integral. So here's another example, and this one's just written as, there's no mention of this being a volume or any region. It's just, here's an integral, evaluate it. So the inner integral has to do with the dx's, because it has to do with the x's because it says dx. So I can integrate this expression with respect to x. So integrating with respect to x, treating y as a constant, that's an add 1 to the exponent, divide by what's up top. And then we're going to go for x, sub in the minus 1 to the top. So there's we integrated with respect to x. Now let's sub in the top minus sub in the bottom. So when I sub into 4x, this becomes 16 minus, when I sub in a minus 1 for x, that's going to be a minus 2y, so minus a minus is a plus. And now the last thing we got to do is just do our integration with respect to y. So 16y, that's going to be 8y squared. Add 1 to the exponent, divide by what's up top. Plus 2y, that's another y squared. And I guess I could have simplified, probably should have, simplified that 16y plus 2y, just made it 18y, but I didn't. I can add it up now to be 9y squared, same difference. But my y goes from 0 to 3. So it's going to be 7 in the top minus 7 in the bottom. I'm thinking of it now as 9y squared. So that's going to be 8y squared. 8 times 9, 72. The whole deal equals 72 minus 0. There's my integral. So mechanically, it's not too bad. And there was no mention of a region, a rectangular region. Although the rectangular region was there, right? If I was to draw this, the x is going from minus 1 to 2, from x equals minus 1 to x equals 2, and the y was going from 0 to 3. So I mean, the region, here I am, oh, I'm still in green. Okay. So x was going from -1 to -1 to 2. So that's the, and y was going from 0 to 3. So we're talking about, I mean, that's our region, the footprint. The z comes out of the board. That's our footprint over which we're integrating, if I'm thinking of this as a volume question. Didn't mention volume, so it was just plain do this integration. Now that I have this thing, you know, now that I have this drawn, there's my y, there's my x's, I could, from, if I wanted to, I could switch the order of integration, do y first and then x. Y goes from 0 to 3, because all the y's always start everywhere through the shape. I start on y equals 0 and I end on the line y equals 3. And then lowest y in the shape, highest y in the shape. So I could switch it if for some reason I wanted to. Okay, let's do another example. Oh, this next example, in this next example, they just give me the region, and it's a dA. So I get to choose whether I want this to be dx dy or dy dx. Because the region is rectangular, I don't think it's going to make any difference. Let's draw that region. So if I'm drawing this region, x goes from 0 to pi. So in here, y goes from minus pi to 0. So this is the region that we're talking about. So I have two choices here. I could pick dx dy, in which case the x's go from 0 to pi, or I could pick dy dx, and the y's go from minus pi to 0, and then the x's go from 0 to pi, and here with the dy's, that's... So either one of these will be equivalent when I do the integration. So why would I pick one over the other? Well, sometimes the integration is easier one way over the other. Let's look at our expression then. So I'm going to go back to here. Let's look at our expression. Is it easier to could I integrate this thing with respect to y first? Yeah, that'd be an add one of the exponent divided by what's up top. Sine x is a constant, so that would just be sine x times all times y. So integrating with respect to y is, I could do that, that's no worries. Could I integrate with respect to x? Yeah, I could. So I don't see any reason to pick one over the other. So I'm going to arbitrarily pick, you know what, I'm going to pick y first. That means I'm doing y first. Y goes from minus pi to 0. And then the outside integration is for the x's, and x's go from 0 to pi. Now I've incorporated that region. Now it's just do this mechanically. I'm going to integrate the inner integral with respect to y. So that's going to be an add 1 to the exponent, divide by what's up top. The x squared is a constant. And that just becomes y times. So there's me. I integrated with respect to y, and I have to go sub in the top minus sub in the bottom. And I'm going from minus pi to 0. So when I sub in, and those are y's, when I sub in 0 for y, I get 0. Zero and 0, so this whole thing ends up being 0, minus, when I sub in minus pi squared is just going to be pi squared, and that's minus pi. So it's minus a minus. So this will become a plus because I'm subtracting the whole thing. Now all that's left to do is integrate with respect to x. So an add 1 to the exponent, divide by what's up top, that 2 becomes a 6. Integrating sine becomes negative cosine. And I have to go from 0 to pi. So sub in the top, when I sub in pi, that's going to be pi cubed times pi squared is pi to the 5th. So it's going to be negative pi to the 5 divided by 6 minus pi. Cos of pi is minus 1, so that's going to make this a plus. Minus, when I plug 0 in, this piece is 0, but cos of 0 is 1, so minus a minus pi, this becomes another plus pi. Whole answer is minus pi to the 5th over 6 plus 2 pi. Let's just clean that up. And I'm not going to put units cubed or anything because this wasn't, the question wasn't presented as a volume. I could interpret it as a volume, but that's me, not the question. Just like when we do regular integration, it's not always area. I could be integrating force over distance and getting work. So it would be in joules, not square meters. Anyway, there's my answer. I'm looking at this and I'm a little curious though. I did the question, got an answer. What if I would have done it the other way around? I mean, I chose dy dx kind of arbitrarily. If I would have chosen x first, would it have been easier? Not like this was hard or anything, but could we have done it, would it even have been easier? If I'd integrated with respect to x first, then this would have been a cosine. And then when I subbed in, it would have been cos of 0 and cos of minus pi. I don't think it would have been any easier. What I was thinking, if it was like when I subbed the trig in, if that trig piece would have been 0, that would have eliminated. But cosine of 0 and cosine of minus pi are numbers that are not 0. So I don't think this would have been any easier the other way around. Let's do one more question. Oh. This one's not too bad, but I'm looking at the integration here. One way I'm going to do a substitution. You know what? I think I would like to integrate this with respect to y first. And most of the reason is because I want to illustrate switching the orders of integration. So that's kind of the main reason why I want to do it that way. Okay, so let's draw the region. The region x goes from -1 to 2, and y goes from 0 to 3. So this is our region. So if I switch this to be a dy dx, then y is going to go from 0 to 3, and x is going to go from -1 to 2. Now, if it looks like when you switch dx and dy that you can just switch the integral endpoints, yeah, that's going to be a rule. That's the next example. That works with rectangular regions. In the next video, we're going to start to look at regions that are not rectangular, and then I got to be a little bit more careful. But so far, this is fine. So I can switch this if I want, and I do, to be dy dx, and we saw that that's just making this switching the 2, 3, -1 and a 0. Now, why did I want to do the y first? Because I think the integration is easier that way. So when I integrate this with respect to y first, that's going to be just straight y squared. And all of those things with x's are constants. And those are y's, 7 the top minus 7 the bottom. So that's going to be a 9 minus 0. So this whole thing is going to clean up really nicely because of that 0. That's what's sort of driving my instinct there to do the y's first. Because when I plug in the 3 minus when I plug in it's going to be -0, so I won't write it. So that works out a little bit easier. Now to do this integral, I could do it by inspection, but I'm going to do it by u substitution because I want to just remind myself of how to switch the endpoints when I do u substitution. So I'm going to let u equal to the x squared plus 3, which means du dx is equal to 2x, or in other words, dx is equal to du divided by 2x. So now when I substitute these pieces in, this is going to turn into a u. The dx is going to be a du divided by 2x. The x's are going to cancel. Okay, great. But now this -1 and 2, those are x's. Let's change everything to u's. That was the point I was trying to make here. When x is equal to -1, u is equal to 4. When x is equal to 2, u is equal to 7. Now, when we cancel out the x's, so let's do that. Let's make that a 9 over 2. I'm having trouble with that. And we canceled out the x's. Now when I integrate, so that's u to the half, that's going to be an add one of the exponent divided by what's up top. So I'm going to get add 1 to the exponent, divide by 2/3, or divide by 3/2, that's the same thing as multiply by 2/3. If I multiply by 2/3, then this just becomes a 3. And I don't have to substitute back now. So this is going from 4 to 7. It's just a straight sub in the top minus sub in the bottom. So and I don't want that to look like it's 37. Minus when I sub the 4 in. Boom, there's an answer. Oh, and I can clean this up a little bit, right? Because to the 3/2, that's going to be 8. Well, I'm not going to. I'm just going to leave it. There, done. Ta-da. So let's formalize the thing that we've already kind of noticed here. If I'm integrating over a rectangle, how do I know this is a rectangle? Well, this must be an x equals a and x equals b, y equals c and y equals d. I know this is a rectangle. So I'll draw it so we have something to point at. But I can read this as, x is going from a to b, and y is going from c to d. So I'm talking about the region being this rectangle. So if I switch the order of integration, I can just switch the endpoints. So if these switch, and that's totally true on a rectangle, but it's only true on a rectangle. So what I want to express with this is, if I switch the endpoints of integration, dy, dx, now the y's go from c to d, and the x's go from a to b. So on a rectangle, I can just switch everything. On a non-rectangular shape, which is in a video coming up, you can't just do that. All right, what's my point with this example? Well, here I've got I'm integrating, but it's a product of two functions, and I've got written there a dA over some region. So here's my point with this. I can choose to write the dA as a dx dy, or I can choose to write the dA as a dy dx. If I choose x first, I'm going to be integrating with respect to x over this region. We don't know what the region is yet, but I know that I'm integrating with respect to x first. So this g of y, that's just a constant. So I could, if I want, bring that outside the integral. Likewise, if I'm integrating with respect to y first, this f of x is a constant. So if I want, I can bring it outside the integral. And then just do this integration first. Whatever I get becomes a function with just y's in it, and then integrate the two pieces. That's all I'm saying there. I could bring it outside. You don't have to. If it's a constant, you can just leave it inside as well. But there are some derivations of formulas in calculus where it's convenient for us to bring that integral outside. One last example. So, and the answer to this is like more of a couple of sentences, a verbal answer, because they're not asking me to evaluate this. They're saying, what is the solid, I guess, whose volume is described by the integral. So the answer is going to be what's solid. Well, let's take a look here. The x goes from 0 to 3. The y goes from 0 to 1. So the answer is, it's I'm trying to draw in 3D, and I don't really draw that well in 2D. So the x, let's run x along this way, and let's run y along this way. So the x goes from 0 to 3. The y goes from 0 to 1. So that's the footprint, and it's some rectangular prism here whose roof that's terrible. Whose roof is given by that function. So describe the solid. It has this rectangular footprint. X goes from 0 to 3, y goes from 0 to 1. And that R is for region, but it's this, it has this footprint, and the roof of it is given by this, a paraboloid, so it's Z equals. That's the volume whose area, if we do this integral, we get. Notice that thing is always positive, so it is like I drew it up like that. You know what? If we let dp graph draw at x squared plus 3, that'll be a lot easier than me. So it's going to be plus 3, and our x goes from 0 to 3, and our y goes from 0 to 1. There, that's okay. That's a lot nicer than having to suffer through my drawings. I'm talking about the shape underneath this graph above that rectangle. That's the shape whose volume is described by.